if we are using CNN from scratch, building layer by layer, or we are already using a model which has learned something, only few layers will be unfreezing it and will be just updating its learning. Okay, so that's transfer learning. Whatever we are using, it will give us some result. The result is what is the accuracy percentage, or not only in percentage, if it's only giving an accuracy number, that with what accuracy it has classified your cancer, whether it is benign or whether it is malignant, what type of accuracy you have achieved. So there will be some numbers. Okay, some numbers. So just this metric is not enough. Got it? Evaluation metrics. The first one is accuracy, which I hope you understood. It will just score how much percentage correct answer you have got. But that is not enough. Fine. So I'm repeating this class. Actually, last class also there were some network issues. So I'm just repeating. So I'll start from here. So what is the problem with accuracy alone? If you give only one number after running your model, and if you want to publish a paper to others, you want to show that I've achieved this percentage of accuracy, what is the issue? Let us try to understand. Now, it is a most intuitive metric. Like every time, like what percentage of marks it got, that is what accuracy is. Now, accuracy is actually a fraction of what prediction you have, fraction of correct prediction. So it is correct prediction upon all predictions, correct plus wrong. All predictions are correct plus wrong. And if you want it in percentage, you can multiply it by 100. Otherwise, it is just a ratio. This is just a ratio number. Okay. But to understand that if you keep accuracy alone, what is the bigger mistake you are committing? So consider you have a data set and you have only like 1,000 tumor patches. Okay, and we are not even talking about images now. We are talking about patches. Patches are the part of images, right? You have only 1,000 tumor patches. Okay, so 1,000 tumor patches. In this 1,000 tumor patches, originally you have 900 benign and you have 100 malignant tumor. Now, suppose what you are doing is sometimes we go to the examination. If you have an objective type exam, you don't know the answer. What you do, I will mark all B's. Sometimes this thought has come in your mind. I'll mark all B's and I'll come back. Let us see what marks I'm getting. So that's what. Suppose that model is not learning anything and it is predicting benign for each and every patch. All the 100% of patch, it is telling that it is benign. Right? Now, if everything is benign, still you're getting 900 correct answers, right or no? Everything without
Yes,
learning
ma'am.
blindly, it is telling all the 900 patches are benign. Still you're getting a 90% accuracy even though your model has not learned anything. So it has never once detected any malignant tumor. So in clinical context, it is a useless model and it is possibly dangerous because you have to know what is, because we are focusing on malignant one, because when it is malignant then only we are classifying as a high grade cancer, right? Benign is just a tumor, just a excessive growth. So accuracy scores, it might look impressive, but in real world it is not having any use. Now when we look at our own class, our own data set, it is highly imbalanced. So in break is 8 tumor subtypes, and in UBC over cancer we have 5 ovarian tumor subtypes. Okay, but each 8 subtypes, they are not equally distributed. Images are not there. Here also you'll see class imbalance is there, right? So when you rely only on accuracy, as you saw, for example, benign and malignant, it was not balanced. 9:1 ratio we had for benign is to malignant. At that time, the model was giving accuracy for benign, even though none of the malignant has been classified. So your model becomes biased if there is no balanced data set, right? So at that time, you'll get a wrong accuracy. So you also need other performance matrices. So the names are F1, recall. Okay. Now for each class also some metrics are there. For overall data set also some metrics will be there, and we will see. Okay. And this will, alongside accuracy, you have to show all these things also. So accuracy is also there, but you should not only be depending on accuracy but other matrices. So when accuracy will work when you have balanced classes. Okay, because all the class will have similar cost and similar penalties. Okay. When accuracy will mislead when your class is imbalanced. So clinical stake. So in when you have, if a cancer subtyping, if it misses a positive patient, he's suffering from cancer, but that cancer has been missed, so there's a loss of treatment and loss of life can also occur, right? So this real world, it will be very dangerous. So but when it comes to paper publication also, what thing you should know, that if only you give an accuracy percentage, it will not be accepted. You have to give other matrices also, like macro F1. Macro means overall data set. And AUC, ROC, I'll tell you what are these: area under curve, confusion matrix. Okay. All these things you have to give. So what are these things? If you don't know, we'll just explore them for now. So what is the rule of thumb? So it is like, if your data set has any class fewer than 15 percentage of total sample, if a class is having very less number of images or patches, and if it is less than 15 percentage of total sample, you should not use accuracy. I will tell you, even if there's a slight uh, 15 percentage, as in you can increase also this number. This is not a rigid number to follow. If I'm saying, even if 15 to 30%, fewer than 15 to 30% of the total samples, please don't go for accuracy. Go for other evaluation matrices also. Okay. And we will see what these are. So first of all, now matrices. What are matrices? Matrix, these are nothing but like a grid of table. Okay. And in every cell some numbers will be there. So this is matrix. Okay. And people who have taken mathematics after 10th, from 11th and 12th only we started to study about matrix. If you don't know about is a matrix, just think it as a table, and each cell is having some numbers. It is an arrangement of numbers in rows and columns. That's it. So a matrix, when it is known as confusion matrix, okay, um, confusion matrix, what it does is, it is showing you what your model has predicted versus what is actually true. So there are two types of positives and negatives. Okay. So suppose your model has predicted positive and your model has predicted negative. So your model could have predicted, some positives which are actually positives. So these are known as true positives. But your model would also look at some of the images and tell them that these are positive images. That means it is malignant images. But in real life, they may not be malignant images. It might make mistake. So at this time, it is known as false positive. Then secondly, there would be some images which are actually negative for malignant. They may not be cancerous. Okay. And it is predicting that they are negative. So what it is in reality, it is predicting that only. So it is true negative. And similarly, if it is negative, your model is not predicting it as negative, it is predicting it as false negative, right? So now you have got the ratio of prediction of, some numbers for true positive, for some number here you will have, and for false positive some number you will have, for false negative over here, and for true negative you have some number here. Okay. So basically it's just a kind of a table, and this table will have some kind of numbers over here representing the ratio of true positive to false negative to true negative. So this is just kind of a table which is giving you confusion matrix, and by the name itself you can understand how much the model has misclassified the images, how much the model was confused while classifying your images. Okay, so this is only confusion matrix. Got it? So moving further.
Yes, ma'am.
So these are the TP, that is true positive. Model correctly predicts the malignant tumor, and tumor also exists. So that is the best outcome that you can get. True negatives, model is correctly predicting it is benign and no tumor is present. What is false positive? Model is saying it is malignant, but actually the tissue is benign. Okay, costly but recoverable. And false negative, what does false negative tell you? That tissue is malignant, but it is saying that no, it is not malignant. So in clinical context, in clinical context. So answer is already here. When I was taking this class last week, I asked people which was for as a biologist, which is the most um, unwanted outcome. So false negative is the most unwanted outcome, because even if false positive has come, suppose a person is healthy but you're predicting that it is cancer, it's okay, because he will go for further test. Okay, and for with the help of this biochemical test, it will say you are not a patient, you are not suffering from anything. That person might become happy and he will go again. But what if it is false negative? That person is actually suffering from a disease, but your model is not predicting. That may incur a higher clinical cost. Got it? So we should, for your project, uh, it doesn't, like don't focus more on false positive. More than that, focus on false negatives. Okay, also focus on false positives, but false negatives are more of concern for you people for this project. Now, I told you that confusion matrix is like a grid like this here, like true positive and false positive, true negative, false negative. So, two columns and two rows. So, two by two. Two columns and two rows confusion matrices was generated. But this was for binary classification. So, what do you mean by binary? Two class classification. But we don't have two class. We have 8 classes in breast cancer data set, and we have got 5 classes in in ovarian cancer data set. So when it is 8 classes, you will have a confusion matrix of 8 by 8. So 8 columns and 8 rows. And when you have 5 subclasses, you have confusion matrix of 5 by 5. So 5 columns and 5 rows are generated. So can you see here a table with
Yes.
the numbers? So this was
Yes.
for so you have to, okay, let us, so see over here, right? X axis has predicted labels and y axis has true labels. So in truth, for malignant phylloid tumor, how much malignant PC is one label, one folder, how much this sample had been classified as benign. So 0. How much malignant PC has been classified as F1. How much malignant has been classified as benign PT1. I hope you got it now. Okay. So like this. So corresponding to rows and columns. So how much? So this one is 17. Okay. So malignant PC to malignant PC, out of all 17s are true positives. This is true positive. This is true positive. So these are true positive only, because you see malignant DC to malignant DC only prediction. So 83 malignant DC. And you see this is a higher number. So higher number is giving you a darker color also. So in confusion matrix, not only the numbers are predicted, but also uh, visually also we can see with the help of colors. Okay, so higher the number, you can set it by yourself. Some set like from lighter to darker they go, some go from blue to reds, whatever color combination you want to give, just you have to explain it from here. So if it is 83 high true positive, you see it's somewhere over here, right? And if it is 9, so the color is from here, somewhere over here. So it is also a kind confusion matrix. When you color code it, it becomes a heat map. What does it become? Heat map. Heat map is nothing but it is showing you with the help, not only with the help of numbers, but also with the help of color intensity. Okay. And I hope you understood that. So coming back to our website. So for UBC ocean data set, confusion matrix between high grade serous carcinoma and low grade serous carcinoma is particularly important to examine. So predicted model was A, B, C, D, E. So first we put it in row wise. We also put that in column wise, A, B, C, D, E. So A to A, B to B, C to C, D to D, E to E. So if it was predicted as A and if it is really A, so here this box will give you that number. If it is B and it is predicted B, this box will give you that number. If it is C and it was predicted as C, this box will give you that number. You see, so in confusion matrix, diagonals you have to see what are the value of diagonals. So that is the true predictions that you have got, correct predictions. But if suppose A, B, C, D, E, A, B, C, D, E. Okay. If I will take this particular box, so it was predicted as C, but in reality it was A. So this is a misclassification. And what is the percentage or what is the ratio of misclassification will be written in this particular box. So like that you can understand. Got it? So
Yes,
when we are
ma'am. Now
going
we got.
to Okay, okay. So now when we will be plotting all those things, and again I will explain, not only in theory, but while doing practicals also, I'll explain it to you again, right? So just leave this one. Don't see UBC ocean and all. So when we are going to do it by ourselves, it will, that intuition will get stronger for you. So now the class is starting actually. So the other matrices are precision, recall, and F1. So apart from accuracy, precision, so to understand what is precision mathematically, it is the ratio of how many true positives, okay, against the total number of positives given by your model. Try to understand, not in the real situation, but what model has classified as the positives. So suppose 1 2 3 4 5 6 7 8 9 10, 10 image patch it is showing as positive. So the total positive given by your model is 10. Out of that it has made some mistakes. Suppose 3, these and these are actually not positive, but it is misclassified as positives. Okay, so these 3 are actually false positive because your model has made some mistake, and by mistake your model has placed it into positive positive labels. So total positive, whether correct or not. So total positives are 10. So I'll keep as in the denominator. If you see the formula, so in the denominator I'll keep 10, and actually true positive. So there are 7 true positives apart from these 3. So apart from accuracy, if you see precision, it is a ratio of actual true positive to all the true positive what your model has predicted. And all the true positive by the model, sorry, all the positives given by the model can either be a true positive or it can either be a false positive. And this false positive is actually a misclassification. This is precision. But we also have another metrics known as recall or sensitivity. So recall is something, the ratio of true positive to all the positives in real life. In real life. So true positive in real also it is positive, but there are some false negatives also. Now false negatives are actually positive in real life but classified as negative by a model. So there's some subtle differences you see. This is all the positive predicted by your model, whether true or false. But here, all the positives in the real life, whether true positive or false negatives. So this is precision, this is recall. And what is F1 score? F1 score is something, but in statistics, there are different types of means. This is a harmonic mean. So how do you get a harmonic mean? Harmonic mean is precision into recall into 2. Okay. So both the quantities 2xy upon x plus y. So this is the formula of harmonic mean. So 2 PR, that is 2 into precision into recall divided by, sorry, divided by precision plus recall. So it is kind of, you want this also, you want this also, and you get a harmonic mean. So apart from accuracy, you also need to give precision, you also need to give recall, and you also need to give an F1 score. Okay. So these are the mathematical explanation of what we are going to use, and these I have written over here. So precision means when I say malignant, am I right? Recall means am I catching everything that matters? Because you see over here in the denominator TP plus FN, true positive plus false negative. So your model has not caught false negatives as positive. So this was misclassification in real world also. This is only what model has caught on that, and it is on all the positives. Got it? So that is why this is known as recall. After precision only, you go for recall. And what is F1? It is the balance of both. Okay. So it will tell you, am I right also and also thorough? Am I also right and am I catching everything? Both the things it will see at once. Okay. Precision and recall, they are near about almost like related. They are different, but the sense of how to evaluate is kind of similar to each other. So again, if you see the this one, precision. So precision is true positive by true positive plus false positive, all the positives given by model. Okay, so here the this one is different for both. So it is true positive by true positive plus false negative. So all the, sorry, false negative. So all the positives that are actually in real data set, so in real world. So they are the intuition is little bit kind of a same, but they are still different than each other. So precision and recall, what they are usually in tension. Why they are in tension? So when you plot them in a graph, when something is rising, for example, if precision is rising, the recall will be falling. Okay, so they are following opposite trends. So as now you also need to have a threshold. Threshold is that you set a mark, a number, a value. Okay, we should not go beyond this. So when there is a flood, no, you see a water level. So this is the threshold. So when the flood alarms must be raised, so when the water reaches this particular threshold and the flood alarms and will be raised. Okay, so like that only you should also have a threshold. What is that threshold? To predict how much positives you are predicting. So if there are more positives, I told you na that on very first example. So if you have 1,000 samples and in that 900 are benign and 100 are malignant, if you are giving positive for benign, right? All everything will be positive. So most you're giving very low threshold for positive. The threshold is like to limit something, you should not go beyond this number, should never go beyond this number. So it is limiting, it is stopping you from going beyond that number. More than certain number of positives we should not have. That means then your model is actually not learning, just randomly telling all are positives. So that is a decision threshold. Suppose your decision threshold is this number, okay, right? So what happens is, yeah. So what happens? Precision and recall. As you lower the decision threshold, when the decision threshold is less, okay, the model will give you more positives. Okay, this is also malignant, this is also malignant, this is also tumor, this is also tumor. It will tell like that. At that time, what happens? At lower threshold, your recall will go up. Recall is true positive by true positive plus false negative, the second one, recall. It will go up, but precision will go down at that time. So when it is going up and when it is going down, it totally depends on your threshold limit. Okay. And what you do actually, when your threshold is less, you will catch more tumors. So that always doesn't mean it is a good model. You're catching non-tumorous images also as a tumor. That doesn't mean that, still misclassification is there. So there is a chance of having more alarms that are actually false in nature. It is not cancerous. It is not cancerous. That is, it is saying that false positives will be more. So this is the first case when you have a very low threshold. Got it? But then that means it is very not a strict model. Okay, the model is not so strict. But if you have a higher threshold, the model is more strict, and it is known as like model is more conservative. The precision will go up, but at that time, whenever the precision is going up, the recall is going down. Okay. So there is no, you cannot have a threshold that maximizes both simultaneously. We want higher number of precision, we want higher number of recall, but it is not possible. If precision is going up, recall will come down. So for that, F1 score and ROC curve are tools for navigating this trade-off. So we want an optimum number, and for that we'll go for F1 score. So F1 score, I told you harmonic mean. So the best F1 score is like meeting somewhere in the middle. Okay. Let us understand interactively, right? Everybody, can you see this? So
Yes, ma'am.
you have set a decision threshold over here. So this I have not published in my website, but if you want, I'll publish it. But you can just see for now. So threshold, what is the threshold for now? 50% you are keeping, like 0.50. 0.50, that is 50 upon 100. So that is 50%, right? Fine. So threshold is this much. And you see, you have got this number, more predicted healthy and less of cancer prediction. Also, you have okay, for healthy patients, you have good, it is a good number. You see, in reality, also they are healthy patients. Only less patients are classified as cancerous. Okay. So this is what? False positive. You understood? You understand this. From the right side of the line, it is like predicted cancer, and left side of this middle line, it is healthy. Blue color is healthy patient, and this magenta color is cancer patient. So this is the area where healthy people should be more. And yes, we have more of healthy people, and some misclassification is there, less of cancer patient. It is okay. Now, what you want your model to be more strict. So, what you will do, you will increase the threshold. You see, am I increasing the threshold? Yes.
Yes, ma'am.
So you see this margin is moving. With the number, let us try to understand. So again with the same threshold, so we have true positive 15, okay, and true negative 14. So the true classifications are higher. So this is, suppose you have made a good model, okay, and still we have got false positive. So false positive also clinically we can, adjust with it, but false negatives, these are our issue, okay. Now what you do is, for just note down the precision. So precision is 0.71, recall is 0.75, f1 score is 0.73, and specificity I haven't told you. At the end we will see the formula is true negative upon true negative plus false positive. So it is playing with the negatives only right now. So till precision recall, we were, playing with positives, and specificity was playing with the negative things, right? So now when I am, so you just see, okay, how these numbers are changing. If something is going up, others should go down. So when I'm increasing the threshold, you see precision is going up and recall is going down, right?
Yes.
And if I am decreasing the threshold, precision is going down and recall is coming up. Okay. So, like this is the problem. So, that is why you should also have these two, but you should also note what is your correct threshold. You have to, have this boundary set. How much area should be this is just a graphical representation. Everything is done mathematically, okay, and your model will only set for you. So we are going to have an accuracy f1 score of nearly like 91 to 0.9, 91 percentage or zero point 0.9. Our ideal like f1 score should be that, okay. To suppose if we want to achieve in this model our f1 score, you see, so it is not reaching. So somewhere in the middle only we are getting maximum number. So if I increase the threshold, then also f1 score is going down, and if I decrease the threshold, then also f1 score is going down. So somewhere in the middle it is balancing both the precision and recall. So just an idea that precision recall, they follow opposite trends. To so balance that, we are going for f1 score. Okay, and somewhere in the very middle you'll get a maximum number, where precision and recall you need to balance both. You have to take care of both. So this is only known as the precision recall trade off, and it is balanced by f1 score and ROC curve. Got it? So what do you mean by macro versus weighted average? So f1 score, you understand, it is a balance of both precision and recall, and mathematically we are taking it as a harmonic mean of both. But now what we have,
Excuse me, ma'am.
yes, yes.
I'm just curious about what could be the full form of F in F1 score. Can you explain?
You want the full forms? Yes, I'll just. So F1
Yeah.
or ROC, AOC, all those, these are the abbreviation for these are the some system. I was about to give you a notes on that. I already worked on it. Let me show you. F1 doesn't have as such any full.
Hariom has answered. Hariom has answered.
No, no, no. Okay, let him answer.
F,
Yes. Actually, F1 is nothing.
okay.
Let me see what he has answered. But F1 is like F measurement. Yes, no full form actually. Correct. F measurement, but no full form. It's kind of like F is for
Okay. Okay.
formula actually. Okay. F is actually formula. No, there's something, we in mathematics, in statistics, there are T test, F test, and what are other, the P values. Got? So these are some,
Yes.
okay, so these are something you should know. So F as such for full form is not there. It's formula F1 we say. Got it? But ROC-AUC, the full form area under curve and all, I'll tell you as I go. I had this in my mind to give you an assignment. That's why I was not. telling you what is F1. And as such, F1 is not having any other full form also. It's just a statistical measurement. F test, T test, and all those things are going on. No full form. Okay. Yeah. I had okay. So this ROC-AUC, you can get over here. So yeah. So I've told you this is the graph. Apart from that, okay, F1, you know what is F1 now. The formula also you know. This is ROC-AUC. So this is, you can see a curve is formed, right? So this is a curve plot of your model. And this actually what trade-off? So balancing, right? True positive rate to the false positive rate. And we are getting a graph, and that graph will be in the form of a curve. So that is ROC curve. So that is ROC, that is receiver operating characteristics curve. And what is AUC? What is the area under this curve? Now, Hariom, I guess you have maths, right? As a background. So you will
Yes, ma'am.
understand. So, you know, when what is actually area under of the curve? Area under the curve. Not only here, area under the curve, what does it signify? Basically, integration, yes? If you see,
Yes, ma'am.
yes, integration.
Integration.
Again, I'm giving a ninth standard example because in the beginning of this session, I gave you a not this session, this whole course, I gave you again a standard example. So in ninth class, when you go and study that chapter motion, in that there is a second equation, S is equal to UT plus half AT square. If you have any brothers and sisters, in your small class, you ask them, how do you derive this? What you do? You take a uniform velocity graph and then you find area under the curve, area under this line, and that will give you displacement. So like that only, area under the line. So not only the values of the curve is important, but also how much area is enclosed in the curve, and this you are getting by integration. Okay. So receivers operating characteristics, whatever your CNN model is operating, right? What kind of characteristics you can learn by the curve. Okay. And what is there in the curve? Inside that, curve, what do you have? If you want to understand, you see, suppose you don't get a curve, but you get a constant line. You get a constant line. See, all this terminology, as you've asked, no, you have to also do it by yourself. Definitely, I want you to go and give that test after the phase 1 is finished, and I'll be scoring you also. Okay, just as suppose if you get a straight line. So what do you mean by straight line? So if you get a straight line over here, let me show you by graph. Yeah. So area of under the curve, it is straight line. That means your model is not discriminating against which is benign and which is malignant. So 50% randomly it is placing in benign, and 50% randomly it is placing in malignant. You got it? Perfect AUC value is 1, but that is not possible. Every positive is ranked as positive and every negative. That means no misclassification. Okay. So the area under this ROC curve, okay. And if you want to know how this curve has been plotted, very easy. In x-axis, the rate of determining false positive against the rate of determining true positive. Those point, if you plot, you will get this curve. This curve can be of any shape, how your model is working according to that. It should never be a straight line. That means random. It should always be above this middle line, only then your AUC value should be more than 0.5. It should be inverted. Any other doubt, Kiran And any other student, if you have a doubt still, if you have understood,
No, ma'am.
if you want me to repeat any concept, then only I'll go further ahead. Okay. So, false positive to false positive rate to true positive rate. Sorry. So, when you plot this, you get some point, some point, some point. These all are generated by the model itself. You're not going to calculate anything. I can get any shape of the curve. Okay. So if you want the value as one, no, in real life, what so what should be the shape of the graph if it is in, so it should be straight line like this. But that is not possible. This is the ideal. So every true positive is following in the true positive, and every false positive will be following in false positive one. That is not an ideal situation. But yes, very less discrimination, so this curve will be very less. Did you understand? So as the mesh classification is increasing, the curve area will be coming down and down and down like this. Still, what we want upper, go up and this. And when we come down here, so is it
I still
possible?
have one question. Uh,
Please tell.
what if a line goes below the straight line?
Below
Will
this,
it
I
be
am coming.
okay or
Yes. No, no, no. I am coming to that. Okay. I'm just coming to that. So,
oh,
like this, it is coming down, down, down. We don't want this flat line also. So if we do, as we are coming down and we are saying this is not desirable, so you see, if the area under curve, that means area under curve is going less and less and less, and we are not getting that matrix. You see over here, as the area under the curve is decreasing, it is performing poorly. Okay.
okay, ma'am, got it.
uh yeah, worse than random. This is random. Equally, okay, suppose you don't want to work today for classification. Yeah, miss it. Very, very good. I'm very happy that Hariom, you have joined our class because you're not from biology background and you are helping others also. Very good. Thank you. Now, when you got a straight line, okay, suppose you don't want to work today and I'm telling you, please place, you have some black pencils and you have some red pencils scattered here and there. Okay, I want you to place black pencils over here, I want you to place red pencils over here. But what you're doing, you don't want to work, you just place randomly some red pencils and some black pencils, some red pencils here, some black pencils here. You're not doing your work properly, so that is random. And what is inverted? Inverted as in you're doing just the opposite. In the black pencil region, you are putting red pencil, just opposite, inverted, worse than randoms. You're swapping your model. Your model is swapping everything here and there. So we don't want these two situations. What is our target? More, we want 90%. Like we want 0.9 because 1% is ideal. Okay. It is telling theoretical it is achievable, but let us see when we work on it. Okay. Since we have a multi-class classification, multi-class ROC-AUC for a multi-class project, so one versus rest strategy. What that means? That means you have class 1, some images here, class 2, some images here, 3, some images here, 4, 5, 6, 7, 8. So how we are going to use? So one versus rest, as in if suppose it is 1, it should not be placed in any of the class versus rest. So if it is placing in any of the class, it will be treated as false positive. All others are negative. Like it is normal thing only, right? You have 8 classes, 1, 2, 3, 4, 5, 6, 7, 8. This patch of image, it should not be going to any rest of any of the classes. It should not fall on any of. So one versus rest strategy. For each class, treat it as a positive class. So when you want to see if suppose now you want to evaluate class number 5. So if that image is following in class number 5, only then it is positive. If it is going classified as any other class, okay, it should be considered as negative. So which one to lead with, AUC versus F1, area under curve or F1? So full form is formula only, right? No other full form. AUC is a threshold independent. So see, when I showed you about F1, just a second, I'll just show you again. Yeah. Can you see this new tab now? So
Yes, sir.
as my F1, as I'm changing the threshold, my F1 score is also changing. So it depends on the threshold. Only in some optimal threshold it can give the maximum number. So our maximum number that we are achieving here is 76%, 0.76. If I'm going and that too as a threshold, not at 5.5, at 0.43 we are getting. Okay, so I'm going slightly on the left side or on the right side, my F1 score, it is depending on the threshold, right? Fine. So at that time my F1 is changing, but AUC is threshold independent. Okay, it will evaluate how well the model is, how model ranks the sample. F1 evaluates performance at a specific threshold, okay, but not AUC. So we'll go for macro F1. Now, what is macro F1? Macro F1 means the overall data sets F1 that you are getting. Usually, what we do now, you just understand. F1 is F1 is calculated for all the classes separately, different numbers. F1 for all the classes separately. But we want one single number, that is weighted average. So that is macro F1. Okay, got it? AUC as a secondary evidence. AUC will be our secondary evidence, and macro F1, not only F1, but we will be calculating a weighted average, and macro F1 will be our, um, you know, the most important metrics. Yeah, I'm just checking the chats. Yeah, weighted average. Yeah, correct. Hariom. So what Hariom has been telling, let me see the chart. Area under the curve represent the total accumulated value of quantity across specific interval. So definitely. So what quantity we had used, that also I've told you. So the quantity that you're referring over here is, the plot against, false positive rate and the true positive rate. We are comparing these two quantities. Okay, fine. So this is also correct, because here, even including me, I am also a person of biology, and most of the other people who are following recording or taking live sessions, most of them, only 2 or 3 people are for CS background. So for them also it is a quite, for me also initially it was very difficult for to understand these things, but it helps when a technical person is there with us, they lead us. So the problem must be broken down into multiple binary sub problems using one of the two strategy, correct? Okay, so basically if I want to um, explain in very layman images, so one versus rest, as in basically smaller portions and we are comparing with others. So there are many algorithms. Okay, so basically you're telling about dynamic programming, Hariom. Here when you are writing like the problem must be broken down into multiple sub problems, so that is basically a definition of dynamic programming, right?
Yes, ma'am.
Mm. But CNN is going to do that by itself. Many biology people, over here, other, have you learned about, do you know about blast? When we are doing sequence alignment, no, multiple sequence alignment, blast.
Yes. Yes,
So
ma'am.
that is also
Yes.
using all these algorithm only, dynamic programming that Hariom in this chat he has told. No, we are so one sequence is aligned to the one sequence only at a time. Then after the both the sequence have aligned, their average has been aligned with the third sequence. So breaking down, so all these things. So let's not go there. Then Hariom at last he's telling for multi-class model that calculates the arithmetic mean, correct, weighted average, right? So for all the classes, F1 has been calculated, and for overall, just get the mean, weighted average, or what we say, apart from mean, average, mean, whatever you want to say. Okay, any central tendency we can take. Fine.
F1 score is for each subclass. And for each class, for example, if there's a breast cancer data set, so you'll get 8 F1 score for each different class. Okay, and if it's UBC ovarian cancer data set, you will get 5 um, F1 scores. And if you take a weighted average or mean, okay, so that overall you'll get for your overall model. Okay, so this is the headline metric, and that headline, as in you have to focus this whenever you are trying to showcase your project work, you can show macro F1. Okay, now this table is important. You can see what is so everything you have to report, but what is more important, it is written, see, F1 and macro F1, and also ROC-AUC. So ROC-AUC also we can plot for per class, and then we can also plot for overall model. Okay, what was lacking in our previous baseline project was, like, we did not include Cohen's kappa matrix. So if I want to tell you, it's just by adding one extra line of code, you can introduce this matrix also. So the formula is observed probability, like the observed result minus expected result upon 1 minus expected. So this is nothing, you don't go deep into this. Basically, it is like an agreement. How much accuracy has been observed, and it is comparing to how much accuracy was expected. So what accuracy is giving you? It's giving you probability. Accuracy is giving you the probability percentage of getting a correct result. But what Cohen's kappa does is, like, it goes beyond that probability, it goes beyond that chance, and it gives you a better agreement. Okay, so it's a better metrics also. And so when you see this, when do you use this particular? So when you want to suppose if you want to show your project to a pathologist, and it will try to this metrics, if you have this metrics and it is giving you a better score, I mean higher the score is between 0 to 1. So higher the score, the better is your model. So kind of like, if Cohen kappa is better, you're comparing it to a pathologist. And apart from, precision and recall, we also have, so recall is known as sensitivity. So the recall is like true positive, ratio of true positive to total number of real positives, I've told you. But there's also sensitivity, that is the ratio of all the negatives. Okay, so this is the true negative rate. How much negatives have been incurred in your, how much wrong your model has predicted. So this is also, so specificity should be, low. The number of negative rates should be lower. So something more about Cohen's kappa is here. So in the paper that we have, uh, referred in our baseline model, we had, so we referred that they had the value of 0.54 to 0.67. And specifically, we saw that in ovarian cancer subtyping. So even if we achieve more than 0.7, then, it is saying that you have achieved a supra, like near to pathologist consistency. Okay, so let us also include this particular metric when we are going to do our work. Okay, and keep in mind that our code after running must achieve a higher value of Cohen's kappa as well, because other all metrics were looking promising. We want to improve that, and in this model we are going to also add this particular metrics. If you publication ready metrics set for your manuscript, so what you want certain tables to add, okay, so tables are like per class precision. You should have a table for all the recalls value, all the F1 value, and this should be separately for your breakage data set and for your UBC ocean cancer data set. Table 2 is macro F1, weighted F1, okay, overall accuracy per magnification level. Okay, so all this table also you need. So what are these things? First table is for per class. For each class, you will make a table, and table 2 will be for your whole model. Okay, and for table 3, so you will have a comparison table. Now don't go with this number, paper number. Okay, whatever we will set some standard reference papers. We'll compare with the previous works that were done. We'll compare our work also, and we'll compare some previous work also, and we'll try to achieve a better result. And the next ones are some figures we'll be having. So yes, I've shown you confusion matrix will be there. Per class ROC-AUC curve should be there. Okay. And training versus validation lost, all these things. So everything actually, graphs will be generated. Okay. So all these graphs that we are going to generate, that also we are going to plot. And it's not optional. We will be adding this Cohen kappa's value, and hopefully if we achieve from 0.6 to 0.7, we'll try to get that. Okay. So moving on further, evaluation mistake. So what mistakes you can make? Certain mistakes. So like now I want to tell you one more important thing is that, so whole data set you will be breaking down. First set will be like a training set. Okay, so the first set is training set. The second set of the sum of the patches will be divided and set into a folder known as training folder, and then second should be testing folder. So then there'll be a second test set. So some of the images you will hide from the model. Your model cannot see this particular images, and it will only see the images from training set. Okay, and whatever it has learned from the training set, it will be tested upon these images. So these test images should not be leaking to the model, otherwise there will be a chance of overfitting. And also few of the images we will be keeping for validation also, so validation test. Okay, so first mistake what you can do is, if you're evaluating things on the validation test, okay, and you're calling the validation test as a test set. So if you're not understanding, don't worry, when we are doing the practicals, I'll repeat this again. So we have to keep all the sets separate. Okay, so we don't want the images to be leaking. Reporting only accuracy on an imbalanced data set. Okay, so this I have already explained you from the very beginning of this session of the evaluation metrics, that if your data set is imbalanced, don't report accuracy alone. You need other matrices also. Then how we are going to split our data, how we are going to stratifying, how we are going to put how much images we have to put into train, how much into test. Okay, so this train test split, this stratification, it ensures, okay, that each split has proportional class representation. For example, in our real data set, suppose one class has a maximum number of images, another class has medium number of images, and the third class has very less number of images. So while splitting also we should keep the proportion likewise. Okay, like it is 9 is to no, I can't say 9 is to, so it can be like 5 is to 4 is to 1. Okay, like this. So while splitting the train and test split also, same ratio of the images must be split in that way. Okay. And so when we are going to do it practically, I'll show you how to do that. So comparing to unfair baseline, so we are using efficient net B0 model. So let us try that only, efficient net B0 model itself. Baselines are like, we'll compare this particular, what you are going to do, we'll compare with our own previous work. Okay, first we'll compare with our own work only, and then only we'll try to find with similar work that already has been done, and we'll compare our work with similar work only. So we'll not make a mistake of comparing whatever CNN model you are seeing online. So you'll be disappointed only. So you should know how you have to compare your work with. Then mistake number 5, no confidence interval or statistical significance. So you should not, what happens is, like, you have to run the same code again and again, and then you have to get, similar kind of results. So if you don't get similar kind of results every time, you don't have any confidence. Okay. So whenever you have a deep learning experiment, it is not sufficient, to run your training. So only one training run. So your result actually depends on the random seed. Those who are not from computer science background, if you don't know what is random seed, let us try to understand what is random seed when we are setting it during coding. Okay. So basically we are giving a starting point to our, code. Right? So don't worry, I'll be explaining it to you in the next week. So run your experiments 3 to 5 times and start with different seeds. And then you report the mean and standard deviation. Then what mean and standard deviation will do is that it will tell how much your result is deviating, from your each in each run, how much you are getting different result. If the deviation is not more, then you had achieved a better result. So you should also have all the metrics, evaluation metrics, plus at last what you're going to do, you are going to run your experiments 3 to 5 times with different sets, okay, with different seeds, and then we'll be comparing the result. Okay. So even if you run only once, okay, so we'll not be running it once, we'll try to run it more than once only. But what it is telling, even if some students, if they want to finish their project very early, and if you want to run once, then you have to mention that in your paper, otherwise your paper can be retracted. So, but it is not better to run your project only once. Okay. So these are some vocabulary that you might have learned. What is accuracy? What is class imbalance? F1 score, AUC, ROC. Okay, test set isolation, which I have just explained it to you, that the images which are in the test set should be completely isolated from the training set. And while training, none of the images from the test set should leak into the model. Okay, so your model should not be able to see any image from the test set. Then what is baseline comparison? What baseline do? Okay, so baseline is like already some work would have been done and you are comparing your work with that, right? So here you see on day 5 paper comprehension, I've given you some annotation. So read more papers. Okay, wait for me to send those papers to you. And also you can read papers, because definitely I'll be asking questions. Please do not just um, come to the live class and see recorded class. No, please do work by yourself also. Some work they are coming, and I would like you to mail me day 5 annotation. Uh, just go and see if you want to see what I'm talking about. Okay, here in the phase 1 on the day 5th. So paper comprehension. And here I had an interactive paper annotation form. So here whatever they are asking, read one paper, fill it over here, click on copy annotation, copy and send, in a PDF format. Okay. So this only you have to do. So that is your task. So I'm not burdening you with more tasks like this. Now here, you should also do one more thing, is you have to click sorry, you have to tick over whatever things, whatever concept you have learned. If any concept that you don't understand, okay, just don't tick it. After, suppose you have understood this accuracy, you have understood precision, okay, you have understood recall. If you have not understood F1, if you have understood, if you have not understood ROC-AUC, leave it. So whatever you have not understood, just click on this, take a screenshot, and that also keep it with you. And we will be evaluating whatever topics you have not understood, and we'll discuss when we are having our practical classes. Okay. So for today, this is enough because all other topics I have taken, and there are two topics like research question. Everything has been covered in between our classes. So I guess the phase one is over.
Let us go and see what is there from the 11th day of our class, that is data acquisition and understanding. I guess this will be here. From here we'll be starting our practicals. Okay. So I'll tell you about the Kaggle, what is API. Okay, then we will decide our folder structure. Then we will look at the class distribution, all these things. Now we'll start coding from here. From next week, we'll be starting our coding. Okay, and tomorrow I'll be completing this particular topic of research foundation and data understanding. Now I want to discuss something with you people. Okay, do you want a skeleton code so that you can refine that code by yourself, or do you want some demonstration of the old baseline code that I have, or can you start it from scratch by yourself? Anyone? Basically this question, Hariom, you start it by yourself? Can you design the complete algorithm by yourself? We'll be using transfer learning efficient net B0.
Ma'am, I
Harsha,
Ma'am, some
don't have.
reference will need it.
you need some reference. And Harsha, what you're saying?
I don't have much like
Okay.
experience in the coding aspect. So I have the
Most of
basics
you don't
understanding
have.
of
So
Python.
what I'm trying to do is, what I'm thinking while coding, we will try to understand the syntax of the code as well. Okay, we'll go slowly. So
Yes,
while
ma'am.
coding, yeah. Also, within it will take 2 to 3 months. Those who are very new in coding, I'm planning to launch a new program for biological students. Now we have biology, so two most important programming language that we should know, that is Python and R. So usually what you do, some people, you get so overwhelmed. You go somewhere, you want to learn Python, you learn Python, and then again you want to go and learn R. Then you learn R again, and you get so frustrated and you think you cannot learn anything. So I'm launching one more program. And what I'm trying to do is, whatever for biological importance, whatever you want to, you should learn for coding, that I'll be posting parallelly in Python also and in R also. So you'll learn Python and R in one go. So the interface will be like this only. I'll be uploading YouTube videos also, and always my website is always free for. I just have to unlock the URLs. I have to make it public. That's it. So you can go and you can learn Python and R, but it won't be so, for CS people, it won't be so helpful. But for people with biological background, it will be very helpful. How to do string manipulation, DNA, RNA sequences, all those things. What are lists, what are dictionaries, and basic syntax. We'll start from basics and we'll go with, harder biological problems. So this is the one series that I'm planning. You can join us.